Welcome back to the deep dive. Today we are taking a really fascinating look at the hidden physics that's, quietly running everything inside your body.
That's right.
We're talking about how water moves, how all those critical ions get distributed, and really why your body's fluid compartments maintain their unique and very specific balance.
And this all comes down to a concept known as the Donnan equilibrium. Some people might know it as the Gibbs-Donnan effect. It's basically the foundational physics that separates a simple beaker of salt water from the living plasma in your veins.
Right. So our mission for this deep dive is to unpack this concept. On paper, it can look a little dense, but its operation is actually, I think, quite elegant.
It is. And if you've ever wondered why your sodium isn't the same concentration everywhere or why fluid shifts happen in the ICU, this principle is the why. It's not just theoretical. This is what drives kidney function, capillary exchange.
And even the stability of the electrochemical gradients that, power your nerves and muscles.
Exactly.
Okay, so let's start with the absolute basics, the components. We're dealing with biological fluids, which are essentially electrolyte solutions.
Right, which is just a fancy way of saying it's water with charged ions in it. You have your positive ones, the cations, like sodium and potassium.
And the negative ones, the anions, like chloride and bicarbonate.
And here's the first absolutely critical rule we have to establish. On a large scale, every single fluid compartment in your body has to be electrically neutral.
The total number of positive charges must exactly equal the total number of negative charges.
Exactly. If they didn't, the electrical forces trying to fix that imbalance would be, they'd be enormous. We're talking forces that could literally rip tissue apart.
So we have this perfectly neutral system, but in the body, it's not one big swimming pool. It's divided up.
Precisely. And that's where we introduce the barrier. The body is sectioned off by what we call semi-permeable membranes.
Like the wall of a blood capillary.
A perfect example. It acts like an incredibly fine sieve. It lets water and small, mobile ions, your sodium, your chloride, pass through freely.
But it's impermeable, completely blocked to the really large molecules.
And that brings us to the star of the show, the ingredient that sets this entire process in motion.
The charged molecule that's too big to get through the door.
That is our non-diffusible ion. In blood plasma, the biggest and most important example is the plasma proteins, primarily albumin.
Okay, and they are trapped inside the blood vessels. You just don't find them in the fluid outside the vessels.
Almost none, yes.
Right.
And crucially, at the body's normal pH, which is around 7.4, these proteins carry a net negative charge. We can just call it pre-minus.
So this fixed, non-moving negative charge trapped on one side of the membrane, that's the whole prerequisite.
That's the entire setup. Without it, you just get simple diffusion until everything's equal.
Okay, let's visualize this. Let's use the classic experiment from the source material, starting with the control group. No protein, just simple diffusion.
Imagine two compartments, C1 and C2. Separated by a membrane that's permeable to everything, we put a sodium chloride solution in C1 and just pure water in C2.
And the outcome is what you'd expect from basic chemistry, right? The sodium and chloride ions just flow down their concentration gradients
until the concentrations are equal on both sides. Sodium in C1 equals sodium in C2. Same for chloride.
And because the concentrations are equal, there's no electrical potential difference across the membrane.
None whatsoever. It's balanced. Delta V is 0. And we can actually prove this with a tool called the Nernst equation.
Right. We don't need to do the math, but conceptually, the Nernst equation calculates the electric potential that's generated just by the concentration difference of a single charged ion.
And in this simple case, since the concentration ratio is 1:1, the equation just spits out 0. The system is electrically silent.
Okay, so now we flip the switch. We introduce the physics that are actually happening inside your body right now.
Yes, the critical change. Compartment 1 now has sodium chloride and our big, non-diffusible, negatively charged protein. Compartment 2 still just has sodium chloride.
And the moment you trap that fixed negative charge in C1, the simple rules of diffusion just get thrown out the window.
They get overwritten. The system now has to find a new asymmetric equilibrium, and it has to obey two absolute laws: electroneutrality in each compartment and thermodynamic stability.
So how does it work? How does this fixed protein force this whole redistribution of the small ions?
Well, you can think of that trapped negative protein as an electrical magnet. It starts pulling on the positive sodium cations, pulling them towards C1.
And at the same time, because it's negative, it's repelling the negative chloride anions.
It pushes them away, out towards C2. The protein isn't just taking up space, It's actively creating an electrical bias.
So to maintain that all-important electron neutrality in C1, it has to suck in more positive charges and push away more negative charges than it normally would?
Exactly. And this forced rearrangement, the Donnan equilibrium, has two key results. First,
The unequal concentrations.
yes, if you measure the ions at this new steady state, they are no longer equal. In the protein compartment, C1, you'll find a higher concentration of the diffusible positive ions, like sodium.
And a lower concentration of the negative ones, like chloride.
Right. Cations are pulled in, anions are pushed out. And second, because those concentrations are now unequal.
The Nernst equation suddenly has something to measure.
Precisely. We establish a non-zero membrane potential. We call it the Donnan potential. It's a direct result of that fixed negative charge.
And the compartment with the protein ends up taking on the same electrical sign as the protein itself.
So since our plasma proteins are negative, our blood plasma is actually slightly electronegative compared to the fluid surrounding it. It's a small potential, but it's always there.
This is where it gets really elegant, I think, because all the different ions, sodium, chloride, potassium, they're all trying to establish their own electrical potential based on their own gradients.
But they're all moving across the same membrane, so they can't all have their own way.
Right, so how does the system stabilize?
They all have to compromise. At equilibrium, every diffusible ion must generate the exact same Donnan potential across that barrier.
And that's where the math gives us this core relationship, the Donnan ratio. We don't need the equation itself, but what does it prove?
What it proves is that the concentration ratio for the positive ions is the exact inverse of the concentration ratio for the negative ions.
Okay, can we simplify that? What's the practical takeaway of the Donnan ratio?
The practical takeaway is this. Cations, like sodium, will concentrate where the protein is, and anions, like chloride, are pushed away from the protein.
So the degree one is pulled in is perfectly matched by the degree the other is pushed out.
It's a perfect balance. And this leads to an incredibly powerful predictive tool, the ion product rule.
The thermodynamic rule of thumb.
Yes. It just states that at Donnan equilibrium, if you take the concentration of the diffusible cation and multiply it by the concentration of the diffusible anion, that product has to be equal in both compartments.
So Na plus times Cl in compartment 1 must equal Na plus times Cl in compartment 2.
Correct. And if those products are not equal, you know the system is not at equilibrium, and movement has to happen to fix it.
Let's slow down and walk through the worked example, because this is where people often get tripped up. We need to see how this product rule actually predicts the direction of movement.
Okay, let's set it up. Compartment 1 has our protein, and initially it has 7 millimoles of sodium and 0 millimoles of chloride.
Okay. And compartment 2, the other side, has 5 millimoles of sodium and 5 millimoles of chloride.
Now we test for equilibrium. We just calculate the products.
In C1, the product is 7 times 0, which is 0.
And C2, the product is 5 times 5, which is 25.
So 0 does not equal 25. We are definitely not at equilibrium.
Right. And we know that to reach equilibrium, we have to raise the product in C1, which means ions must move from C2 into C1.
Now, this is the counterintuitive part. To raise that product from 0, we need both sodium and chloride to move into C1. But wait, why would the negative chloride ion move into a compartment that has a big negative protein repelling it?
That is the beautiful conflict that this resolves. The system is so driven to achieve that thermodynamic equilibrium, to make the products equal, that this drive can temporarily overcome the local electrical repulsion.
So even though the protein is pushing chloride away electrically,
The overall thermodynamic need to balance the ion product is stronger. So some chloride is forced to move from C2 into C1 against that electrical gradient.
okay, so chloride moves into C1.
Yes, and the very instant that negative chloride enters C1, it threatens the sacred rule of electroneutrality.
So a positive ion has to follow it immediately to keep the charge balanced.
Exactly. A sodium ion immediately follows the chloride from C2 into C1 to maintain that charge balance. So this simple product rule reveals the entire complex direction of movement.
That clears it up. It's a sequence driven first by thermodynamics, then instantly corrected by the need for neutrality. Okay, so we've established this complex, asymmetrical, steady state. What does this deep dive actually mean for your body's health?
The clinical relevance is profound. We can boil it down to 3 critical consequences. Number one is fluid balance, which links directly to something called oncotic pressure.
Okay, so we established that the protein compartment, the plasma, ends up with a higher total number of particles, right?
That's right. You have the protein itself, that's one particle, plus you've pulled in an excess of positive ions and pushed out some negative ions. The net result is always more total solutes in the plasma. This creates osmotic pressure.
And water always follows the highest concentration of solutes.
So there's a constant osmotic pull of water into the protein-containing plasma compartment. This pressure is what holds fluid inside your blood vessels.
And that specific pressure, the part caused by the proteins, is what we call oncotic pressure.
Precisely. It's a key part of the Starling forces, which govern whether fluid leaks out of your capillaries into your tissues or gets pulled back into the blood.
This connects directly to edema, to swelling. If your oncotic pressure drops, fluid rushes out.
Absolutely. Think about a patient with severe kidney damage. They often lose huge amounts of plasma protein in their urine,
So they lose that fixed negative charge, the Donnan effect collapses.
and the oncotic pressure, that fluid-retaining force, just vanishes. Fluid floods out of the blood vessels and into the tissues, causing widespread edema. This physics explains that clinical sign perfectly.
Wow. Okay, so what's consequence number 2?
It contributes to the overall resting membrane potential of your cells.
So while we think of nerve signals being about sodium and potassium channels.
Right, those are the fast-acting parts.
Yeah.
But the Donnan potential is the foundational backdrop. All your cells contain large, negatively charged, non-diffusible molecules, proteins, DNA, phosphates,
And those fixed negative charges inside the cell create a Donnan effect.
that contributes to the steady negative electrical environment inside all your cells. It sets the stage for the faster ion gradients to do their work.
And the third consequence, this one ties the physics to the body's chemistry.
It's all about pH and acid-base balance. This is a really powerful connection. Remember we said the protein's charge depends on the pH.
Right. At our normal pH of 7.4, the proteins are negative and we have a strong Donnan effect.
But what if the pH were to drop? Say during a severe metabolic crisis, acidosis. The protein would start binding more hydrogen ions, more Hs+.
And that would reduce its overall net negative charge.
Exactly. And if the protein becomes less negative, the force pulling in sodium and pushing out chloride gets weaker.
So the strength of the Donnan effect itself is constantly being tweaked by your acid-base status.
It is. A change in pH means a change in the electrical environment. And that means a fundamental shift in how water and ions are distributed. It connects everything.
So the Donnan equilibrium is this fundamental physical rule that guarantees the distribution of ions and water across our membranes is unequal, and that this inequality is absolutely essential for life.
The difference between a simple salt solution and a living organism really rests on that impermeable negative charge.
Thank you for sharing your source material for this deep dive. It really shows how simple physical rules can drive such incredibly complex and critical biological outcomes.
It was a pleasure.
Now, to leave you with a final thought to mull over, one that connects this physics directly to a clinical outcome. We said that if a patient loses protein and develops severe edema, the underlying problem is a collapse of the Donnan effect. So why would simply giving that patient intravenous saline, just salt water, often fail to fix the swelling? Giving them more salt should, in theory, pull water back into the vessels. Why doesn't it work effectively when the underlying problem, the loss of that non-diffusible protein, remains unaddressed? Something to think about.